Welcome to chapter 5.6. We're going to work through the separation of variables solution for our one-dimensional transient heat transfer problem. So, just a reminder, our governing differential equation at the last step had been non-dimensionalized to this form where we've got the second derivative of theta with respect to c equal to the first derivative of theta with respect to tau. So we're going to do the same very presumptuous move that we did in our last chapter and assume that there is a separation of variables solution such that theta, which is a function of both xi and tau, can be defined by a function capital X that only depends on xi and a function capital Y that only depends on tau. So if we roll with this, we'll start differentiating theta with respect to each parameter. So the first derivative with respect to xi, y is effectively a constant because y does not depend on any way in xi. And if we differentiate again, y is still just a constant with respect to xi. And so we just have the second derivative of this function x with respect to xi squared. We do the same thing for the function y. We differentiate theta with respect to tau, and x is a constant this time because x does not depend on tau, and we get the first derivative of y with respect to tau. So these are the two ones we're going to need to plug back into our governing differential equation up here. And if we do that, we get an intermediate form of the function, and we'll carry that over to the next page and then divide through by both x and y, and that brings all of the x terms over to the derivative with respect to xi, and all the y terms are on the same side as the derivative with respect to tau. That is our separation of variables as we defined it last week. And we know that in order for this to be true, we need these two sides of the equation to equal a constant. And we call that constant lambda squared, and it can be positive or negative. In this instance, we'll define it as negative so that when we pull it over to the opposite side, it's positive. So if we do that, we can separate out our first ordinary differential equation, and it's a second order equation with the linear term in x, and the linear term has a positive coefficient, and so this is a Sturm-Liouville problem, and the solution to this, we can just write it down. It's a combination of sine and cosine functions. So that's the solution for x, which is our first ordinary differential equation. Coming back here, we'll look at our y term. So we can write our y differential equation, which is linear first order and it's homogeneous. It's a separable equation, so we could separate it out and integrate it, but we've already done that several times in chapters 2 and 3. So I'm just going to write down the solution here. It's an exponential, and the argument of that exponential is negative lambda squared times tau. And again, there's a constant of integration c. So we have the solutions to each of the ordinary differential equations that comprise our separation of variables solution. But in order to apply the boundary conditions for a particular solution, we need to transform our boundary conditions into this new xy nomenclature. And so just a reminder, the function we're looking at for theta is x of xi times y of tau. And so if we write each of these boundary conditions as a multiplier of x and y, for the first one, xi is 0, so that's x of 0, and tau can take any variable on the range, so that's just y of tau, and that equals 0. Either of those terms could equal 0 to make this expression mathematically correct. In fact, both of those terms could equal 0, it would still be mathematically correct. But that doesn't make it physically correct. If we said that y of tau equals to 0. That basically means there is no time dependence of the solution, which is incorrect. There is definitely a time dependence. So the physical situation constrains what we can do with the maths, and we have to say instead that x of 0 is going to equal 0. And that enables us to retain our time dependence in the solution. Similarly, for the second boundary condition, either x of 1 can equal 0 or y of tau can equal 0. If y of tau equals 0, we lose the time dependence. So we'll choose x of 1 to equal 0. The last condition, the initial condition, we don't make too much progress here. We just fill in the numbers and that's what it is. So our next step is applying these boundary conditions to the separated ordinary differential equations. We'll start with the spatial equations because those two boundary conditions are homogeneous, so we think they'll probably be easier. First boundary condition, x of 0 equals 0. So if you plug that in when the argument for sine is 0, that whole term becomes 0. When the argument for cosine is 0, the cosine term becomes 1, and so we're left with the expression b equal to 0. That means there is no cosine term in our solution. Next, we apply our second boundary condition. Plugging that in, we have that 0 equals a times sine of 1 times lambda. And we have two unknowns, a and lambda, one equation, so we can't solve for them both. But as we saw last week, a can be 0 or sine of lambda can be 0. If a is 0, that means x of c equals 0. That removes our spatial dependence. Mathematically correct, but not physically correct. So a cannot equal 0. That means that sine of lambda has to equal 0, and that is true when lambda equals any integral multiple of pi. We start with 1 pi rather than starting with 0, because if lambda equals 0, we get a linear solution, which is not physically realistic. So that's why we start with the index n equal to 1. And writing our x solution, we now have something that's looking useful. We plug in n pi for lambda, this should be a c, and we are tempted possibly to go ahead and start applying the initial condition to our expression for y of tau. But before we do that, we should recombine the x and y expressions so that when we solve the combined solution, we know that the initial condition is being applied to the entire solution, not just the temporal part of the solution. So we'll go ahead and do that. We'll plug in what we have now for x and what we have now for y, and we get the full solution for theta. There's two constants of integration, and like last week, we can combine them into a single value since it's just a value that we're going to solve for. And that gives us our expression for the solution to the 1D transient heat equation. N can be any value between 1 and infinity. And again, we face this problem. Well, if the solution can be any value of n, which value of n do we choose to get the actual physical solution? We don't just want a mathematical solution, we want the physical solution. And so we'll leave off there and pick up and discuss the orthogonality and superposition we use to finish this problem off. Thanks.